Hi, so welcome to my talk today, which is called Large Area Constrained Wilmot Surfaces and Asymptotically Schwarzschild 3 Manifolds at the 5th Geometric Analysis Festival in the special session Higher Order Variational Problems in Geometry. So before I start, I would like to thank the organizers for making this happen and for giving me the opportunity to speak today, which is a great pleasure for me. To make sure that we're all on the same page, I would like to start with a bit of background, and the first thing I'm going to talk about are so-called asymptotically flat manifolds. So we're going to consider a connected complete Riemannian 3 manifold MG that has integral scalar curvature R, and then we're going to say that such a manifold is asymptotically flat if outside of a compact set it looks very much like Euclidean space. So more precisely, we're going to require that there is a non-empty compact set K such that the complement of this compact set K is diffeomorphic to R3 minus a bore, and such that in so-called asymptotically flat chart, we can write the metric G as the sum of the Euclidean metric plus some perturbation sigma, where sigma decays like mod x to the minus 1. Alright, so one reason why such spaces are interesting is because they arise as initial data of isolated gravitational systems for the Einstein field equations. So the picture you should have in mind is of a space-time with a limited number of large masses, such as stars and black holes, but little matter apart from that. So an observer who moves very far away from these masses is going to feel very little gravity corresponding to the space-time and also the initial data set being asymptotically flat. And now in this physical context, it turns out that the scalar curvature doesn't only have a geometric meaning but also a physical one, because it provides a lower bound for the energy density of the initial data set. So in particular, for the initial data set to be physically viable, the scalar curvature should be non-negative. Alright, so to get a feeling for such asymptotically flat manifolds, let's consider an example, which are going to be initial data for a static black hole, which is the so-called Schwarzschild solution. And in order to define this space, we're going to consider a positive number m, which is going to correspond to the mass of the black hole. And then the space is given as R3 minus the ball of radius m over 2. And the metric G is given as the so-called Schwarzschild metric, which is 1 plus m over 2 times mod x to the 4 times the Euclidean metric. Okay, so it's easy to see that this space is asymptotically flat, and there's a few things that you can check. So first of all, the boundary of the space, which is the sphere of radius m over 2, is a closed minimal surface, and this closed minimal surface corresponds to the horizon of the black hole. And moreover, you can also check that the scalar curvature of this manifold vanishes, which corresponds to the fact that the Schwarzschild solution is a vacuum solution. So there's no matter outside of the black hole. Alright, so here you can see an illustration of the Schwarzschild space. You can view this as a two-dimensional shadow of the three-dimensional initial data set. And as you can see, the further you move out to infinity, the more flat the space becomes, whereas the closer you get to the horizon, the more curved the space becomes. Alright, so in today's talk, we of course would like to consider more general spaces than Schwarzschild manifold. However, many of the results that I'm going to present aren't going to hold for the large class of asymptotically flat manifolds. And for this reason, we're going to define a smaller class of asymptotically flat manifolds, which are asymptotically flat manifolds that asymptotically look like a Schwarzschild black hole. And we're going to call them asymptotically Schwarzschild manifolds. So more precisely, we're going to require that in the asymptotically flat chart, we can write the metric G as the sum of the Schwarzschild metric with mass m plus some perturbation sigma, where sigma now decays like mod x to the minus 2. Alright, and for the statement of one result, we're going to require that mg is in fact a small perturbation of Schwarzschild. And by that I mean that this perturbation sigma doesn't only decay like mod x to the minus 2, but is also smaller in the scale of its decay. So in formulas, we're going to require that the lim sub as x tends to infinity of mod x squared times the modulus of sigma is less than the small constant eta. Alright, so for the Schwarzschild space, we've seen this parameter m, which corresponds to the mass of the black hole. And also over here we have this number m, which somehow corresponds to the mass of this space. And if you have a general asymptotically flat manifold, it turns out that there's also a well-defined notion of total mass, which is given as 1 over 16 pi times the limit of the following flux integral over a large coordinate sphere as the radius of this coordinate sphere tends to infinity. Okay, so there's some physical motivation why you would consider this quantity, because this quantity somehow measures the flux of the metric at infinity, which you can view as the gravitational flux at infinity. However, just looking at this quantity, there's no reason to believe that this is well behaved in any sense. However, we have the following fundamental result due to Shane and Yao, and also later on due to Witten, which is known as the positive mass theorem, that if the scalar curvature of mg is non-negative, so if the energy density is non-negative, so is the total mass, and equality holds if and only if mg is flat R3, so if the space-time is empty. So from a purely qualitative point of view, this mass seems to be well behaved. Okay, so now that we've found this good notion of total mass, one important problem in mathematical relativity is you can also find a good notion of local mass. And one possibility to do so was put forward by Hawking, and he introduced a quantity that we now call the Hawking mass. And in order to define this quantity, we're going to consider a closed two-sided surface sigma whose mean curvature is equal to h. And then the Hawking mass of the surface sigma is defined to be the square root of the area of sigma divided by 16 pi times 1 minus 1 over 16 pi times the integral of the mean curvature squared. So again, there's some physical motivation why Hawking considers this quantity, and in fact he expected it to be a measure of the strength of the gravitational field in a domain enclosed by sigma. From a more mathematical point of view, some of you might recognize this integral over here to be 4 times the Willmer energy, which is this quantity down there, which plays a very important part in many areas of mathematics. Okay, so to get a bit of a feeling for this Willmer energy and also for the Hawking mass, let's consider an example, which is going to be flat Euclidean space. And here you can prove the following. So if you have a closed surface sigma, then you can show that the Willmer energy is always greater or equal than 4 pi. And equivalently, you can also show that the Hawking mass of the surface is always less or equal than 0. And equality holds if and only if sigma is a round sphere. Okay, so this is a very fundamental fact about the Willmer energy, and it's also quite easy to prove, so let's quickly do this together. And I'm going to call the principal curvatures of sigma kappa 1 and kappa 2. And then of course the mean curvature is given as, the square of the mean curvature is given as the square of the sum of the principal curvatures, which you can rewrite as the difference of the principal curvature squared plus 4 times the product of the principal curvatures. And the product of the principal curvatures of course equals the Gauss curvature k. So now for this reason we can estimate the Willmer energy from below by the integral of the Gauss curvature over the part of the surface sigma that is positively curved. And now, as you might recall, the modulus of the Gauss curvature corresponds to the area element of the Gauss map of the surface sigma, so of the outward normal. So in order to estimate this from below by 4 pi, all we need to show is that the Gauss map of the surface sigma attains every point on a unit sphere at a point of positive curvature. But in order to see this, all you need to realize is that every coordinate function on a closed surface attains a local maximum. Okay. So from a mathematical point of view, this is of course a nice rigidity result. However, from a physical point of view, this is somewhat troubling. Because the Euclidean space is flat, so you would expect 0 local energy and not negative local energy. And for this reason, it seems that the Hawking mass is only a viable measure of the strength of the gravitational field if the surface sigma is in some sense special. Okay, so in the case of the Euclidean space, these special surfaces are the round spheres. However, now if we're given a general asymptotically flat manifold, it might not be so easy to find these surfaces anymore. However, there's at least 2 possibilities to find such surfaces, and the first class of such surfaces are so-called area-constrained Willmer surfaces, and these are going to be the protagonists of today's talk. So as the name suggests, these surfaces arise as area-preserving critical points of the Willmer energy, or equivalently as area-preserving critical points of the Hawking mass. And in particular, these surfaces are potential candidates to contain a maximum amount of Hawking mass given their perimeter. And for this reason, it is very immediate why these surfaces should be well adapted to the Hawking mass. And now, of course, this variational problem also comes with an Euler-Lagrange equation, which is that the Laplacian of the mean curvature plus the product of the mean curvature and the length of the trace's second fundamental form squared plus the Ricci curvature of the outward normal nu plus some Lagrangian parameter kappa coming from the area constraint is equal to 0. And what I would like you to notice right now is that this equation over here is 4th order. Okay, so as I said, there's also a second class of surfaces that are well adapted to the Hawking mass, and these are so-called stable constant mean curvature surfaces. So as the name suggests, the mean curvature of these surfaces equals a constant scalar, and in fact these surfaces arise as stable critical points of the area functional under volume constraint. So in particular, these surfaces are potential candidates to bound the maximal amount of volume given their perimeter. And now what's more important for us is that Christodoulou and Yao have shown that if the scalar curvature of the ambient manifold is non-negative, so is the Hawking mass a very stable constant mean curvature surface. So as you might recall, the scalar curvature corresponds to a lower bound for the energy density, so it seems that from a purely qualitative point of view, the Hawking mass of such stable constant mean curvature surfaces seems to be well behaved. Okay, to again get a bit of a feeling for these surfaces, let's consider an example again, which is going to be the Schwarzschild space. And in the Schwarzschild space, you can prove the following. So if the Schwarzschild space is rotationally symmetric, and one consequence of that is that if you take a coordinate sphere centered at the origin of a radius larger than m/2, then the sphere is symmetric in the sense that it has constant curvature. And now by direct computation, you can show that all of these spheres are stable constant mean curvature surfaces and also area constrained Willmore surfaces. And also what's very immediate to see is that the family formed by all of these spheres forms a foliation of all of the Schwarzschild space. Okay, and now there's a few more things that you can check. So if you compute the Hawking mass of each of these spheres, this turns out to be equal to this number m over here. And this is of course the quantity you would expect because these spheres enclose a black hole that has mass m, and apart from that there's no matter in the Schwarzschild space because it's a vacuum solution. And moreover, you can also compute the barycenter of these spheres, which is of course equal to the origin, and the origin corresponds to the Hamiltonian center of mass of the manifold. So somehow these spheres seem to capture the physics of the Schwarzschild space in a very canonical way. And now with all of these nice properties, you might ask if these spheres are unique in a certain sense, and the answer is yes, because Brentle has shown that the spheres of symmetry are the only embedded closed two-sided constant mean curvature surfaces in Schwarzschild. Alright, so now that we have such a nice description of the Schwarzschild space in terms of stable constant mean curvature spheres and also in terms of area constrained Willmore spheres, we might ask the following questions. So if we have a general asymptotically flat manifold, or manifold is asymptotic to Schwarzschild, first of all, can we show that there is an asymptotic foliation by stable constant mean curvature spheres, area constrained Willmore spheres? And the reason why I'm only asking for an asymptotic foliation here is that in the definition of an asymptotically flat manifold, we've excluded this compact set K. And we've made no restrictions on what the geometry or the topology of this compact set K should look like. And for this reason, it might not be reasonable to expect such a foliation to exist globally. In any case, once we've established the existence of such a foliation, can we also show that the leaves of the foliation are unique in some global sense? And as before, this is probably only going to hold under some additional largeness assumption. And finally, can we also show that these spheres detect the physics of the initial data set in a canonical way? So can they somehow recover the mass, the center of mass, the asymptotic energy distribution, and so on? Okay, now it turns out that for stable constant mean curvature spheres, all of these questions have been studied quite extensively. And one reason why these problems have been studied earlier for stable constant mean curvature surfaces is that the corresponding Euler-Lagrange equation is second order, so from a purely analytical point of view, they're somewhat easier to study. And in particular, we have the following result. So if we have a manifold that's asymptotic to Schwarzschild with positive mass, with a well-defined center of mass and non-negative scalar curvature that satisfies the following growth condition, that the modulus of x squared times the scalar curvature is radially non-increasing. So this just means that the energy density radiates away at a controlled pace as you go to infinity. Then you can prove the following. So for every sufficiently small number h, or positive number h, you can find a large stable constant mean curvature surface sigma h, whose mean curvature equals h. And the family formed by these theorems forms a foliation of the complement of a compact set of M. So we have the existence of an asymptotic foliation. And then we also have the strongest kind of uniqueness result that you could expect, because what you can show is that every closed stable constant mean curvature surface of sufficiently large volume has to be part of this family. And finally, it seems that this foliation is also very well adapted to the physics of the manifold Mg, because it can show that the barycenter of these spheres sigma h asymptotes to the center of mass as these spheres grow larger. Okay, so Husken and Yao were the first ones to study the existence of asymptotically the existence of asymptotic foliations by stable constant mean curvature spheres of asymptotically Schwarzschild manifolds, and they also proved some preliminary uniqueness result. And this uniqueness result was then later on strengthened by Jing and Tian, by Brendle and Eichmeier, by Carlotta Chodos and Eichmeier, by Chodos and Eichmeier, and eventually by Eichmeier and myself. And now, and also I should say that the statement about the center of mass is due to 1. Now, of course, you might ask if a similar result holds for general asymptotically flat manifolds, and it turns out that you can prove weaker results for asymptotically flat manifolds, but at least in this generality, the theorem is not true, because there's examples of Carlotta and Shane of asymptotically flat manifolds with positive mass and non-negative scalar curvature that contain a Euclidean half-space. So in particular, within this Euclidean half-space, you have infinitely many large stable constant mean curvature spheres enclosing any volume that you're going to require. Alright, so now that we've talked about large stable constant mean curvature spheres, let's move on to area constrained Wilmot surfaces. And here it really turns out that the problem is more difficult, because for a very long time the following result due to Lam, Metzger and Schulze, who were also the first ones to study area constrained Wilmot surfaces in the context of relativity, was the strongest available. So they showed the following. They considered a manifold MG that is asymptotic to Schwarzschild with positive mass and assumed that this manifold is a small perturbation of Schwarzschild. So again, this means that the lim sub of the modulus of x squared times the modulus of sigma is less than a small constant eta as x tends to infinity. Okay, and this assumption they showed that for every sufficiently small number kappa, which is also positive, you can find a large area constrained Wilmot sphere sigma kappa, whose Lagrangian parameter is equal to kappa, and that the family formed by these spheres forms a foliation of the complement of a compact subset. Okay, so this result is of course a very important step in the right direction. However, there's a few issues with it. So first of all, the assumptions on the manifold are quite restrictive, because if this number eta is very small, the result might actually only cover a very small class of asymptotically Schwarzschild manifolds. And also the theorem doesn't really provide you any uniqueness statement, at least it doesn't provide you any uniqueness statement that goes beyond what's implied by the inverse function theorem. And finally, it also doesn't tell you anything about the asymptotic positioning of the foliation, so it doesn't tell you if these spheres center around the center of mass or if their positioning is governed by something else. Okay, so now before we try and remedy these issues, we should maybe compare stable constant mean curvature spheres and area constrained Wilmot spheres a little bit and see if we can even expect the same kinds of results. And the first comparison I want to make is going to be in the Schwarzschild space, and it's regarding the variational nature of the spheres of symmetry. So in his thesis, Bray has shown that the spheres of symmetry are in fact isoperimetric. So if you regard these spheres of symmetry as stable constant mean curvature spheres, they in fact solve the variational problem they arise from. Okay, now if you regard them as area constrained Wilmot spheres, this is surprisingly not true, because we have the following observation. That you can find a sequence of spheres in Schwarzschild whose Hawking mass converges to infinity as I tends to infinity. And in particular, the spheres of symmetry are not area-preserving maximizers of the Hawking mass. Okay, so this might be a bit surprising, so let's take a look at what's going on here. So the dotted line over here corresponds to the horizon of the Schwarzschild space, which, as you might recall, is a minimal surface, so in particular its mean curvature vanishes. And now if you take multiple copies of this horizon and move them outwards slightly, so as in this example you take 3 copies, then the mean curvature of each of these copies is still going to be very small. Now what you can do is that you glue small minimal bridges between these copies to obtain a connected surface, and then the Wilmot energy of this glued together surface is still going to be very small. But it now has about 3 times the area as the horizon. And iterating this procedure, you can produce a surface of arbitrarily large Hawking mass. So in particular, it seems like the Hawking mass is not very well behaved in the presence of a minimal surface. So if we want to prove something reasonable about area-constrained Wilmot spheres, maybe we should only consider surfaces that avoid a sufficiently large compact set. Alright, so this is the first difference I wanted to talk about, and then the second difference is the role of stability. And for a constant mean curvature surface stability is a pretty strong property, and this is already apparent in the flat Euclidean space. Because Barbosa and Docamo have shown that if you have a closed stable constant mean curvature surface in R3, it has to be a round sphere. Now for Willmore surfaces, such a result is far from true, because Bauer and Kubert have shown that the exist stable Willmore surfaces are very genus in R3. And in particular, these Willmore surfaces also minimize the Willmore energy among all surfaces of the same genus. So in particular, what this means is that stability is not enough to classify Willmore surfaces to be round spheres in the flat Euclidean space. However, on the other hand, we also have the following result due to Kubert and Schätzle, that if you have a closed Willmore surface in R3, which is sufficiently round in the sense that its tracer second fundamental form is small in L2 sense, then the surface has to be a round sphere. So if you would like to prove uniqueness of large area constrained Willmore spheres, maybe rather than asking them to be stable, we should require them to have a small tracer second fundamental form in L2 sense. Okay. So now with these additional assumptions at hand, can we prove a stronger uniqueness result? And in my thesis I proved the following result. So I considered a manifold Mg that is a small perturbation of Schwarzschild, so same assumptions as those by Metzger and Schulze. And then I proved the following. So I considered a sphere that avoids a large convex set K, so this is the first additional assumption, and then I assumed that this sphere has small tracer second fundamental form, so this is the assumption replacing stability. I also required that the surface has large area, which is the assumption replacing large volume, and then I also had this additional technical assumption that if you rescale this sphere to unit area, then its barycenter is very close to the origin in the asymptotically flat chart. Okay, so under these assumptions I could show that the Hawking mass of the surface is less or equal than the total mass, so the variational degeneracy of the Hawking mass goes away if you only consider this class of surfaces. And moreover, what I showed that if sigma is an area constrained Willmore surface, then it belongs to the foliation constructed by Metzger and Schulze. Okay. So this result, of course, improves upon the uniqueness result by Metzger and Schulze. However, it still comes with a lot of drawbacks. So first of all, we still only consider small perturbations of Schwarzschild. And moreover, we have this very unnatural centering assumption over here, which I'm going to explain to you shortly why this would help. Okay, so here's an illustration of the theorem. So the cross marks the origin in the asymptotically flat chart. And the surface on the left is round in the sense that the L2 norm of the tracer second fundamental form is very small, and it's also very centered with respect to the origin in the asymptotically flat chart. So the previous theorem would apply to this surface over here. Then the surface on the right is still very round, but now its barycenter would be somewhere over here, whereas the origin in asymptotically flat chart is very far away, so the previous theorem wouldn't apply to the surface on the right over here.